All right, we are in the home stretch, 7.2. We're going to be revisiting our old friends, arc length, area under the curve, surface area, but we're going to do it in the environment of parametric curves. So think back to calculus 1. So one of the main topics there was just computing a derivative. So we're going to do the same thing here, but we're going to do it on a parameterized, I can never say it, whatever. We're going to do it on a parametric curve. So the form is, if we're given x as x of t and y as y of t, then the first derivative is just simply y prime over x prime. So you can think of that as a really small change in height over a really small change in width, rise over run. It's slope. Tangent lines are just the slope of that line, slope of the curve at that one point. So let's do a few examples here. So for A, then x prime of t will be 2t. And yt given as 2t minus 1 means that y prime of t is just 2. dy dx is y prime over x prime. That's just going to be 2t over 2, just kidding, 2 over 2t, which is 1 over t. The other thing that we do when we take derivatives is we're really interested in determining where any critical values are. So critical values occur when the derivative equals 0 or the derivative is undefined. And that's true when we learn it for the first time in calculus 1, and it's going to be true here. So our critical values, c dot v, so dy dx is never 0, right? There's nothing I can plug into dy dx, which is 1 over t. It's never 0. But I do have that dy dx is undefined at t equals 0. So I have a critical point at t equals 0. So if I were to graph this, and remember this thing looks like a sideways partial parabola. When t is 0, let's see, I'm at the point x 0, y of 0, which is when x is 0, sorry, when t is 0, x will be -3. And when t is 0, y will be -1. So that's just right here. And so that is why the tangent line is undefined. So the tangent line, or the equation of the tangent line at this critical value is given by x equals -3. That's the equation of the line. So this is when t equals 0. The next example, B, we're given that x of t equals 2t plus 1, and y of t equals t cubed minus 3t plus 4. And yes, we are given these limitations here on the t values. I'm not going to worry about that right now. Oh, sorry, actually I am. Notice that because that example really quickly. Because t was in the interval -3 to 4, it's a valid critical point. Like if we had gotten t equals 7 for our critical value, it's not in the interval, so it's extraneous. All right, so for B, back to B. So -2 to 5 is my interval. I want to compute the first derivative, dy dx. So I need x prime of t, which is 2, and then I need y prime of t, which is 3t squared minus 3. So I'll get for dy dx, 3t squared minus 3 over 2, which, you know, I'll just leave it like that. Okay. So our critical values when I have a fraction and I'm saying, okay, this ratio or this fraction is equal to 0, the only thing that can make that true is the numerator. So I just need to figure out when is the numerator going to be 0? Well, when t squared is 1. So I just get that t equals plus or minus 1. And then I also need to check I guess instead of saying where, I should say when dy dx is undefined. And that happens never. So I have my critical values, or at least my t values that will give me critical points. And I noticed that t being plus or minus 1 is in the interval. They're both in the interval -2 to 5. So I get 2 critical points. I get x of 1, y of 1, and then I get x of -1, y of -1. So when t is 1, I'll get 3, and then 2. And then from -1, I'll get -1, and what would that be? -1 plus 3 is 2, 6. I probably should have done that on paper before saying it in a recording, but okay, double check me. I've been known in the past to make really silly mistakes, and some not so silly mistakes. All right, so those are our critical values, t equals plus or minus 1, which brings us to our critical points, which I computed hopefully correctly. Time will tell. All right, last example. X of t is 5 cosine t, and y of t is 5 sine of t, and then our interval is 0 to 2 pi. So again, just going to compute x prime, which is -5 sine t, y prime 5 cosine t, so I'll get dy dx as 5 cosine t over -5 sine t, which is -5 cotangent t. I need to find my critical points. So I just need to figure out, basically, undefined means the denominator 0, derivative being 0 means the numerator is 0. So let me scooch this down. Okay. So my critical values are when dy dx equals 0. So that's going to happen when cosine is 0. And cosine of 0 happens at t equals pi halves and t equals 3 pi halves. I also need to check where the derivative is undefined. And that's going to be where sine of t is equal to 0. So that's going to be t equals 0 and t equals pi. So hopefully this is making intuitive sense, because if we think about this graphically, if I graph x of t and y of t on 0 to 2 pi, I'm going to get a circle, which is very hard to draw. Oh, that's not bad. Okay, so now I have this circle, and I'm starting here. This is where t equals 0, so I'll be at the point 5, 0. And then this will be at t equals pi. And so this parametric curve just travels around counterclockwise, full circle. So if we're thinking about the derivative, well, a 0 derivative means you're flat, right? So here would be a 0 derivative. So dy dx equals 0 at t equals 1/2, right? So that's right here. This is t 1/2, pi half. This is t equals pi half. And you would also have the same thing down here at 3 pi over 2. Right, which is exactly what we got here and here. And then for the undefined bits, we can see that that's going to be where we have our vertical tangents. Right, so dy dx is undefined at t equals 0, and it's also undefined over here at t equals pi. And so that's what we got here. So first derivative, done. So now let's actually just do an example where we're going to find the equation of a tangent line to the curve given by the parametric equations. So this is the same thing. You're just going to, remember, if you want to find, just in general, if you have a function, this is like Cal 1, right? You have a function, f of x equals y, and you want to find the tangent line to it. Right, and this is some point A. So if this is A, then this is f of A, and the slope of this line is just the derivative of f evaluated at A. So then the equation of the line is just in point slope form, y minus f of A equals f prime of A times x minus A, right? Point slope form. My favorite way to construct a line. Takes the least amount of effort. And when you do y equals mx plus b, it's cool if you already have the y-intercept, but if you don't, it's like just extra work. Why? Why? All right. So we need to kind of follow the same process. We need to find the derivative evaluated at the time given. All right, we have a given time here. This is kind of like our A, right? So I have x prime of t will be 2t, y prime of t will be 2. So I get that dy dx equals 2 over 2t, simplifies to 1 over t. Then, here's some notation if you haven't seen this before. If, before we have f prime of something, and so I just stick in that A, and that signifies to everyone, hey, I'm evaluating the derivative at this specific value A. Well, I don't really have that notation here with dy dx, so usually you draw a long vertical line, and at the bottom, you'll just write t equals whatever you're given, t equals 2. And so that signifies to the reader that you're evaluating the derivative dy dx at t equals 2. So this equals 1 over 2, okay. Then we also need the point. So this is our slope. And we need a point. So x of 2 equals, what does it equal? 4, 1. And y of 2 equals 3. So our point that we're using is 1, 3. Therefore, the equation of the tangent line at time t equals 2 is just y minus the y point equals the slope, which was 1/2 times x minus the x point. So if you want to convert that to y equals ms plus b, great. I will try not to judge you too much, but you can definitely leave it like that. I apologize in advance if it prompts you for y equals ms plus b, and I will try to change it if I catch it. All right, let's talk about second order derivatives. So we took the first derivative, what a thrill. Let's talk about the second derivative. So it's not as simple as y double prime over x double prime. Do not, try to not. Okay, pen, you're back in action. Try not to fall into that trap. So you can read through the book about, well, it's posted here too, but you can go to the textbook if you'd like to kind of dive into it a little bit more. This is the derivation of it. I like to write it less in line, kind of hurts my eyes. So d squared y over dx squared, don't think about squaring as like an exponent on a number. It's just saying take the derivative of y with respect to x 2 times. So, right, this is the second derivative of y, wrt, with respect to the variable x. And so this is going to be ddt of dy dx over x prime of t. Right, so dx dt is the derivative of x with respect to t. So I can write x prime of t. ddt of dy dx is just I forgot where I was in my sentence. Anyway, okay, so dy dx is still a function of t, right? We just did a bunch of examples like that. And so it makes sense to say, okay, I'll take the derivative of whatever that guy is with respect to t. So let's do an example. I'm going to need to compute x prime and y prime, simplify that, and then take the derivative of that simplified thing with respect to t one more time. So x prime of t is 2t. Y prime of t is 2. So that gives me that dy dx equals 1 over t. Now that I'm here, I can go ahead and take the derivative of dy dx with respect to t. So this is your first derivative. Then I'm going to mosey on down the line, and I'm going to take d dt of 1 over t, right? So 1 over t was dy dx, and I'm going to put that over x prime of t. So the first derivative of 1 over t is just negative 1 over t squared, and the first derivative of x prime is still 2t. Right, so now this is my second derivative, and if I simplify it, I'll get negative 1 over 2t cubed. So this is my second derivative. All right, so now we're going to go into area under a parametric curve. So before, when you were in Cal 1, oh, just kidding, at the beginning of Cal 2, which was like what? I know it was probably only 3 or 4 weeks ago, but it feels like a long time has passed. Okay. Da-da-da-da-da. You have your function. Okay, I want to know the area under the curve. Super. So I just like make these little rectangles and I estimate, you know, the area under the curve doing these little rectangles, and then, okay, then we get Riemann sums and et cetera and so on. I need to do the same thing with parametric equations. So this would give you, you're going to sum up the area. So these little areas are just f of x times delta x, right? This little change in x here. And then the whole thing, the integral is just f of x dx. So I need to do the same thing with parameterized. You know what? I'm going to stop even attempting saying that word. I don't even know what it's supposed to be, what's right. Maybe it is right. Who knows? If I have a parametric curve, then this is given by x of t and y of t. And if you go to the book and look at their derivation of this formula, there is a typo in there. And it's not just like one typo. It's like it keeps popping up and it makes it really hard to follow. So I apologize on their behalf, I guess. Oh, we're going to do the same thing. You're going to make these little rectangles here to estimate your area. Okay, so this is some little x sub I minus 1, and then this is x sub I. Okay, so this is some partition, and then the height here is going to be y of what? Is it x? No, this is actually not x in here because I don't have this, right? So remember, y equals f of x in this situation. So this is f of x, and you know, this is x here. But now what's happening is that this is actually x at some point ti minus 1. So we're kind of like peeling back an onion layer here. So not only do we have a small change in x, that small change in x, because x is continuous, really reflects a small change in t. So this is really x of t sub I minus 1 to x of t. So I'm just going to do the typical thing where I'm just going to let this be x of t I star, where t I star is just somewhere in the interval from t to I minus 1 to t to I. T sub I, sorry. So it's just some time, I have a little window of time, a little teeny tiny baby window of time, very small, calculus small. And I'm just saying that ti star is just some specific singular point of time in that window, in that interval. And so I'm going to use that to determine my height, because if x is happening on this window, then y is also happening on that window as well. So I'll just call this ti star. Okay, super. And then this area of the rectangle is just the space times height. So it's going to be y of ti star, the height at some time in that interval, times the width of the rectangle, which is x of ti minus x of ti minus 1, right? So base times height. And then I do something very fancy. I multiply by 1. I would say that if anyone here is pursuing a degree in math, like where you're going to be doing a bunch of proofs and whatnot, you should expect to multiply by 1 and add 0 in the most unusual ways, because a lot of proofs are done that way. All right, so this was a very sneaky multiplication by 1. So multiplying by 1 is nice because it doesn't change the value or the truthfulness of an equation. So multiplying by 1. And then notice in the brackets here, x of t sub I minus x of t sub I minus 1 over t sub I minus t sub I minus 1. This is, when you see this, you should be thinking, oh, that looks like a difference quotient. Okay, wait, difference quotients become derivatives. Okay, that's the calculus brain in action. So if you want to sum up all these areas, so this is going to become, I'm not saying it's equal to because it's not, but as our partitions get very, very small, very fine, then this really becomes just y of t times x prime of t. And the small change in the t, we call that dt. And then I want to add up all these rectangles. And the fancy calculus way we add stuff is with this fun symbol, boom. So that's it. That's the derivation, a very hand-wavy version of the derivation of how we find the area under a parametric curve. Notice it's right there. All righty. So let's use it. Find the area under the curve of the cycloid defined by the equations, blah. So this is what they look like. So I just want to find the area of the shaded region. So in order to do that, I'm going to set up my integral. I'm going to go from 0 to 2 pi, right? Because that's what's given here. 0 to 2 pi, 0 to 2 pi. Then I have y of t, which was just 1 minus cosine of t. And then I need x prime of t, which is 1 minus cosine of t. So I get 1 minus cosine of t. So just to be extra clear where all of this is coming from, this is the derivative of x. This is y. And then I have to throw on my dt because of that cool trick I did earlier. Alrighty. So we're just going to expand, work our trig magic, and integrate. So this becomes the integral from 0 to 2 pi of 1 minus 2 cosine t plus cosine squared t dt. And because I can't integrate cosine squared of t as is, I'm going to rewrite it in the following way, which you will remember from earlier in the semester. right? So that's that substitution. And then you can always derive it for yourself by remembering the mantra sine, cosine, cosine, sine, cosine, cosine, sine, sine. All right, I guess, yeah, I can just go ahead and integrate now. So I'm going to get t minus 2 sine t plus 1/2 t plus 1/4 sine 2t. And I'm evaluating that from 0 to 2 pi. So simplifying this, I'm going to get 2 pi minus 0 plus pi plus 0 minus 0 minus 0 plus 0 plus 0. And so the area under this curve is 3 pi. All right, so next we want to do arc length. So remember that arc length previously, when f of x was given, we just had that arc length was the integral from whatever, a to b of 1 plus f prime of x squared dx. And so now you can think of this like, okay, so if x of t was just t, right, this dummy parameter, don't make me say it, dummy setup for how to write this as a parametric curve, then y of t would just equal y of x of t, right? And so dx dt would just be 1, and dy dt is just y prime of x times x prime of t. And so with this setup, you could kind of move through the flow of how it becomes this in the setting of a parametric curve. So what we're really just saying is that you go from your start time to your stop time, square root of x prime of t squared plus y prime of t squared dt. So let's go ahead and compute some arc length. All right, so we need to find x prime and y prime. So we have that x prime of t is -3 sine t. So that will give us that x prime of t squared is 9 sine squared t. So I need x prime of t squared and I need y prime of t squared. So next up is y. And so I end up with 9 cosine squared. And now, so this is my starting time, this is my stop time. And just to kind of guide us, like, so this is really just a semicircle. Okay, that's awful. Better. So this is a semicircle centered at the origin with radius 3. So the circumference, or the arc length, should be 1/2 of the circumference, which should be 1/2 times 2 pi r, which is 1/2 times 2 pi times 3, which is 3 pi, right? So this is the easy third grade way to compute the arc length, except we call it the circumference of a circle, and then we divide it by 2. Now we're going to do it the hard way. All right, so I'm going to go from 0 to pi of the square root of 9 sine squared t plus 9 cosine squared t dt. And so the radicand will simplify to just square root of 9, which is 3. So I'm going to get the integral from 0 to pi of 3 dt. And guess what? Yeah, 3 pi. Alrighty. So the last thing on our list today is surface area. So we remember surface area as 2 pi times the radius and then times the arc length. So we want to convert this to fit a parametric curve. And so we're going to do it very much the same way as we did before. So remember that this was arc length, and then the 2 pi and the f of x joined together to become the radius. So we're definitely going to do the same thing here. So 2 pi, but now our radius is going to be given by y of t. So this is our radius, and this is our arc length. Okay, so with that, we are going to find the surface area of a sphere of radius r centered at the origin. So this is a surface of revolution in the following way. So you have, I'm telling you, a circle really is the hardest thing to draw. And I feel like a half circle is even harder. Okay, so this is us, the semicircle. Well, okay, let me back that up. We want to find the surface area of a sphere. The way that I get a sphere from a surface of revolution is I take a semicircle and I rotate it about the x-axis. Right, so now I have this little globe now. Oh, you know what actually is harder than drawing a semicircle is drawing 2 semicircles to join up to be 1 actual circle. Always say. So this is what I'm doing. Boop, boop, boop. Great. So remember that you're just taking this little arc length and you're multiplying it by the circumference. And that's going to give me my whole globe, my sphere. So if I want a circle of radius r, I need to have x of t be r cosine t, and I need y of t to be r sine of t. And because I only want the top half of the circle, I need to let t go from 0 to pi, not 2 pi. So then, now that I have this set up, so this is the semicircle. Okay, super. Now I'm going to just kind of plug everything into our form for surface area. So I need y prime and x prime. So x prime of t is negative r sine t. Y prime of t is our cosine of t. So if I square those, then x prime of t squared is r squared sine squared. And similarly, I will have y prime of t squared being r squared cosine squared. And I just love to add sine squared and cosine squared because it equals 1. So now I'm going to go from my start time to my end time, 0 to pi. Then I have 2 pi y of t, which gives me my circumference. And y of t was r sine t. And then I'm going to multiply that by that little width of arc length, which is r squared sine squared t plus r squared cosine squared t, and integrate with respect to t. So this simplifies so nicely. I get 0 to pi, 2 pi r squared sine t dt, right? Because the square root just becomes r, so I combine that with the r from 2 pi r, and I get 2 pi r squared sine t dt. Remember that r here is a constant. So if you're like, oh, integration by parts, no. R is a constant. We only really have to deal with sine of t. And in fact, to illustrate that, I could write it like this. So the integral of sine of t is just negative cosine. And I'm going to evaluate that from 0 to pi. So I get 2 pi r squared. So cosine of pi is -1. So I get negative 1 minus -1. That is hideous. Okay, so that's 2. So this is 2r squared times 2, which is 4 pi r squared. And this certainly is the formula to compute the surface area of a sphere of radius r.